Students, in last class we have discussed about mirrors, drawing the ray diagrams and finding out the image location. We talked about magnification, the lateral magnification, we derived the formula for that, and we have seen how to locate the image when an object is given on the principal axis or above the principal axis, not on the principal axis. So, we have discussed about these cases. So, we will now start with a question based on what we discussed in the previous class, and then we will move on to the next concept. So, the question given is like this: an object is placed 20 centimeters in front of a concave mirror and the image formed is double the size of the object. Find the possible radius of curvature of the mirror. So, that is the case. So, we already have derived a formula for magnification. Here they have given that the image which is formed is having a size double the size of the object. So, which means the magnification is 2. But if you observe carefully, they have not mentioned anything about whether the object, the image formed is an inverted image or an erect image. So, it could be anything, and that is the reason why they are asking you the possible radius of curvature, because there are two possibilities depending on whether you consider the image formed to be an inverted image or an erect image. So, let us see how to analyze this situation. So, we know the expression for magnification we have derived already, and instead of using the minus v by u expression which we know, because we need to find the radius of curvature which can be linked with the focal length of the mirror. So, what I am going to do is I am going to use the formula which has the f term in it, the focal length in it. So, which is f by f minus u. So, that is the expression for magnification which we have seen. So, in this particular expression, so as I told you, the value of this can be taken as plus 2 or minus 2, because they just told that the image formed is double the size of the object. They have not told whether it is inverted or erect. So, that is the basic idea. So, I will solve for the two cases separately. So, let us solve for the two cases. So, first I will assume that the value of f by f minus u is plus 2, and then I will assume f by f minus u is minus 2, and I will find the value of f in both the cases, right. So, in this case if you observe, so we need to substitute the value of u. So, it is given that the object is placed in front of a mirror which is at 20 centimeters. So, what is the value of u I should be substituting here? Is it 20? No, because it is in, we know that if the mirror is something like this and if the object is over here in front of the concave mirror, so we should always be considering this as negative u, right. So, because the light rays will be going in this direction, but the object is on the other side, correct. So, I should be considering it as minus 20. So, while substituting the values, I should be writing it as f by f minus minus 20 is equal to plus 2. So, simplifying this expression, you would be getting f is equal to 2 times f plus 20, and so solving this you will get f is equal to minus 40 centimeters. And I guess you are all aware of what this minus sign indicates. Minus sign would be the focal length, I mean the focal length of a concave mirror should definitely be a negative value, because the focus will lie on this side itself, wherever it is, it will lie in front of the mirror. So, which means it is on the opposite direction of incident rays. So, that is why we have a negative sign. So, I have told you this earlier, concave mirror will have a negative focal length and convex has positive focal length. Okay. So, this is one possible value of f. So, we will see the other one. So, solving this will give me f is equal to minus 2f, or let me substitute the value of u, minus 2 into f minus minus 20. So, solving this will give me f is equal to minus 2f. Here we will have plus multiplied by minus will become minus. So, minus 40, and simplifying that further will give me f is equal to minus 40 by 3 centimeters. Okay. So, I got the focal length in both the cases, but the question asks me to calculate the radius of curvature, and you all know the relation between radius of curvature and focal length. So, it is just the double of this, right. So, for this to happen, we can say that the radius of curvature should be equal to 80 centimeters. That is one possible value, and for this case we can say that radius of curvature should be 80 by 3 centimeters. So that is the basic idea, right? So that way you can use the expression for magnification. What I want you to do is I want you to think about how the ray diagram would be in this case. So for a mirror which is having a focal length of 40, if I am placing the object at 20, it basically means that the object is placed between the focus and the pole. So let me call this as case 1 and this one as case 2. So I will draw a ray diagram for one of these cases. I want you to draw the ray diagram for the other case. I will draw the ray diagram for the case 1. I want you to draw the ray diagram for case 2. This is same as what we have done earlier. In the last class we have drawn the ray diagrams for different positions of objects. I hope you remember that. We have taken a concave mirror, we have divided the principal axis into 4 regions, and depending on which region the object is present, we drew the ray diagrams and we found the nature of the image formed. So what I am going to do now is I am going to draw the ray diagram for case 1. I want you to complete the ray diagram for case 2, right. So let us see the ray diagram once. So in this case we have the focal length as 40 centimeters. So I will take a concave mirror. So this one has a focal length of 40 centimeters. So let us say this is where the focus is. Now if you look at the object which we have placed here, the object is placed at 20 centimeters. So it is here. So object is exactly halfway between the focus and the pole. So this is where the pole is. So this is where the focus is. So you all know that this is basically the first case which we discussed during the ray diagram. So whenever the object is placed between the focus and the pole, the image is formed behind the mirror. A virtual image is basically formed. So in this case, I will just extend this. You can take any 2 rays, draw the ray diagrams and find the image location. So I will take one light ray which is passing through the focus and incident on the mirror, right. So this is the incident ray which is passing through the focus, and you know that after reflection this light ray should become parallel. So this light ray becomes parallel. It reflects parallel to the principal axis. You can consider one more light ray. I will take another light ray which is passing through the pole, which is directly incident on the pole. So whatever is the angle, I can say that at the same angle I can take one more reflected ray which would be like this, right. So these are the 2 reflected rays which we have. This is one and this is the other. So when I extend them backwards to find the point of intersection, that is where the image will be formed. So extending backwards and extend. So extending them backwards, I will be getting the location of image. So which is somewhere over here, and this is where the image is formed. So that is how the ray diagram looks like for case 1 which I have given you. So you can easily see that the image formed is a virtual image, and it is an erect image as well, and that is the reason why we got a positive magnification. So positive magnification, you all know what it means. So the positive value indicates that whatever is the orientation of the object, image also has the same orientation, right. So here when you took negative sign, you would obviously get the image to be an inverted image. So please draw the ray diagram for this scenario just like how I have drawn in that particular case, right. So earlier we have discussed about lateral magnification, so which we represented with M, right. So it is basically the ratio of the dimensions of image and object perpendicular to the principal axis, right. So now we are going to talk about longitudinal magnification, and this would be the ratio of the dimensions of image to object along the principal axis. So if there is an object which is placed along the principal axis, so let us consider a mirror. So we will consider a case where there is an object which is placed along the principal axis, right. So what I am going to do is, let us say there is an object somewhere over here, a point object, let us say O, and the image is, let us say, over here at I. Now let us consider a scenario where that object moves by a small distance, a very small distance. Let us say it has moved in this direction towards left and it has reached this position. Let us call it as O dash. So object O has moved to a different position. So we can easily expect that the image which is formed here will also move slightly, right? For now we do not know which direction it moves, whether it moves like this or whether it moves like this. So let us just represent it with some direction over here. So what I will do is I will represent that the image has moved like this to this position I dash. Now think properly here. So when the object was at O, when the point object was at O, the image is at I. So for O, image is I. When the object moved to O dash, the image moved to I dash, right? It means that, can I say, if there is an object between O and O dash, let us say this is an object which is placed, so this one here is placed between O and O dash, can I say that the image of this will be formed between I and I dash, right? Instead of considering it as a point object moving from here to here, let us consider an object having this much length. Then can I say that the image formed will have this much length? Is that correct? So that is exactly the method which I will be using now to understand longitudinal magnification. So what I am going to do is, I will take the mirror formula, which is 1 by u plus 1 by v is equal to 1 by f, right. So now I will just differentiate that expression. You will understand why I am differentiating it in a while. So when I differentiate this expression, the derivative of this, I can write it as minus 1 by u square into du. So du by u square with a negative sign. I will differentiate this. When I differentiate this, I will get minus dv by v square. Similarly, I will differentiate focal length as well, right. So here I will be getting, or focal length of the mirror which we have taken will be a constant value, right. For a particular mirror, I am changing u and v values, correct. So focal length is fixed, which means it is constant. So when I differentiate this, I will be getting 0. Okay. Now, so think of it like this. Let us say the object is initially at a distance of u and it has moved by a small du, right, and the image is at a distance of v and it has moved by a small distance of dv. That is what happens. That is how we understood it earlier, right. So the object when at u, image is at v. When the object moved to u plus du, the image moved to v plus dv. So can I say that if the object which I have taken has a length of du, then the image will have a length of dv. Can I say that like that? Please observe carefully. What I am understanding here is, if the object's length is taken to be between O and O dash, which is du, I can say that the image length will be formed between I and I dash, which is dv. That is the concept which we will be using in this particular scenario. So I will just rearrange the terms to find the value of dv by du, which is image length by object length. So when I rearrange the terms, I get, you can see I can cancel minus and minus. So dv by du, if I find out, I will be getting the value as minus of v square by u square. So that is the expression which I get. So you know that this expression I can once again rearrange it as, if I can take this minus sign out. So this I can write as v by u whole square, or I can also write it as minus v by u whole square. So when squared, this minus sign will anyways become positive. So if you see this expression, so this expression here is what we call as longitudinal magnification. And when you look at this term which we have over here, so the one which is inside the bracket, you already know what this term here represents, that is lateral magnification. Lateral magnification. So, that is the basic relation between longitudinal and lateral magnification, but keep in mind, if I have to use this particular formula which is like this, m long representing longitudinal magnification is equal to minus of m square. So, when I just write m, it generally means lateral magnification. So, I do not have to specify that, but whenever writing longitudinal magnification, make sure to represent it. So, whenever you see just m, so that is normally lateral magnification. So, this is the basic expression which we get. Now, as I told you, this expression during the derivation, you can see that I have used du and dV. I have found the relation between dV and du, which are very small lengths, infinitesimally small lengths. So, which means this formula is applicable, it is applicable only for very small lengths of object and image. So, you can't use this for long objects. So, you can't keep a pen in front of the mirror like this, which is having this much length, and use that formula to find the length of the image of the pen. Clear? So, if the object is having a very small size placed at a particular location, then you can use this particular formula. So, think once again, if I place a very long object, then different points on this will have different u, different object distance. If u value is different, m value will also be different, correct? So, you can't apply that for long objects, extended objects. So, it is applicable for only very small objects, and that is what we have used in the derivation also. You can see that all these are infinitesimal lengths, du is an infinitesimal length, dv is an infinitesimal length. So, this is applicable only for very small objects. So, now you may get a doubt, how do we do for a long object, how do we do for an extended object if the object is having sufficiently long size which is comparable to the mirror's dimensions. So, in such a scenario, how do we find magnification? So, we will see that now. Now, let us see how to find the magnification of an object which is sufficiently long, which is placed along the principal axis. So, let us say this is the concave mirror, some focal length f, and the object is along the principal axis. Let me mark few positions. So, let us say this is focus, center. So, let us place an object on the principal axis, right. So, what I will do is I will place it like this. So, let us say this one here is the object. So, it is sufficiently long, you can see its length is comparable to the focal length of the mirror. So, let us consider that the length of this is some f, the length of the object is also f. Okay. And one of its ends starts at center and it extends further away from the mirror. So, this is the case given to us, and now you will have to find out the length of image. So, this is what we will have to calculate. The focal length of the mirror is f, the magnitude is f, you know the sign, because it is a concave mirror, the sign should be taken as minus f whenever we are substituting it in the equation, right. Okay. So, the object is between the center and this position. Okay. So, now let us find out how the image is formed. So, here we can consider that whenever we have an extended object, you know this already, that we can take the two ends as 2 point objects, find the location of images of the 2 point objects separately, and between those two images will be the actual image of this object, right. So, I will use the same concept. I will consider this end as one object, let us call this as A, this end as another object, let us call it as B, and I will find the image of A and B. So, wherever the images are formed, between those two will be the actual image of this extended object. So So, two objects, right. So, object 1. So, object 1 is at A, correct, which is at center. So, when it is at center, so we know that the object distance is this much, which is minus 2f, and you know why it is minus, because it is in front of the mirror, right. So, minus 2f. So, we have discussed this already. When the object is placed at the center of curvature, the image formed will also be at center of curvature. If you want, you can also write the equation to verify that. 1 by u plus 1 by v is equal to 1 by f. This is the actual equation, general equation. So, if I substitute the values, if I substitute u as minus 2f plus 1 by v is equal to, this is 1 by f with a negative sign because of concave mirror. So, when you simplify this, you will get the value of v as minus 2f. So, u is minus 2f, v is minus 2f. So, it means that the image of A is formed at the same position wherever the object is placed. I mean, if the object is placed at the center, then the image is also formed at the center itself. See, you can understand this by a very simple idea also. See, if we have a mirror like this, with this as the principal axis. So, let us say we have this particular point here as the center of curvature. The reason why the image is formed at the same location is because if I consider an incident ray like this, what happens to the incident ray? Because it is coming from the center, it reflects back. Take another light ray. Same thing repeats once again. It is also coming from the center, it gets reflected back. Now, look at the reflected rays, which are the same two lines. Those two reflected rays once again meet at this particular position. So, this is the location of the object, that is also the location of image. So, this is one very important thing which you will have to keep in mind. The image and object coincide when the object is placed at center of curvature. So, this is a very important result. It will be useful for us in the later discussions as well. Okay. So, we have talked about one position. So, we know that the image of A, let us call it as A dash, is formed at this position itself. So, I will write it down here only. So, this is also the location of A dash, right. Now, I need to find out the location of B dash. So, I will once again write the formula for object 2. So, for object 2, so tell me what is the value of u for object 2. You know that this length is f, this is f, this is f. So, totally 3f. Because it is in front of the mirror, I should be substituting it as minus 3f. So, when I substitute the values, I get 1 by u plus 1 by v is equal to 1 by f. So, substituting 1 by minus 3f, which is minus 1 by 3f, plus 1 by v is equal to minus 1 by f. So, simplify that, you get 1 by v is equal to 1 by 3f minus 1 by f, and solving this is going to give you the final value as 3f by 2 with a negative sign, right. 3f into f by 3f minus f, which is this. So, this is the expression which you are going to get, minus 3f by 2. And where does minus 3f by 2 lie? So, it is exactly between the center and focus, which is this point, right. So, which means the image of B is formed at this position. So, this is B dash. So, which means the image of the whole length of the object will be between A dash and B dash. So, I can represent it like this. So, that would be the image. So, if this is the object, the image is this. So, one important thing you will have to observe here is that the image is reversed. I mean, the image is in the reversed manner. If the object, let us say, is like this. So, if let us say this is the object which is like this, with this end as A and this end as B. Now, if you look at the image of this, it is formed in this manner, right, it is reversed. Now, this is something which you can understand from the earlier derivation also which we have done. If you remember, earlier we have understood that longitudinal magnification is equal to minus m square. What this means is, irrespective of m, whatever be the sign of m, longitudinal magnification is always negative. Longitudinal magnification is always negative. So, a very important point this is. So, what that means is, longitudinal magnification we have defined it as dV by du. It means if dV is positive, du is negative. So, all the lengths are measured from the pole. So, if V, or let us say if u increases, then V decreases. So, what I mean to say is, if you come back to the point object analogy, if an object moves from A to B in such a way that u is increasing, then the image A dash will move from A dash to B dash such that V is decreasing. Clear? That is what you will have to understand from here. So, if object moves away from the mirror in this particular case, the image moves towards the mirror in this case. So, the object and image should always move opposite to each other. So, that is what this negative sign indicates, and that is a very, very important thing which you will have to understand. So, I will write it down here also. So, what it means is that object and image always move opposite to each other. Opposite to each other along principal axis. So, that is the basic idea. So, whenever we have an extended object along the axis, so make sure that you consider them as 2 point objects, find the location of images of the 2 point objects, and the actual image will be formed between those 2 image locations. So, that is what we have seen. Oh, I did not, we can also find the length of the image which is formed here. So, you can easily say this is minus 2f, this is minus 3f by 2. So, this length, I will write it down here, length of image is equal to the distance between these two, which is f by 2. So, this is the only way you can find out the image for an extended object. Clear? So, for a small object you can directly use that formula. For an extended object, this is the method which we should use. We will solve a question now based on longitudinal magnification. So, if you see a small object of dimensions 1 millimeter by 1 millimeter, so it is basically a square, is placed 30 centimeters in front of a mirror having a radius of curvature of 40 centimeters. Find the area of image formed. So, that is the question. So, they are asking if this is the object in front of a mirror, you need to find where the image is formed and the size of that image, the dimensions of that image, right. Now, one important thing which you will have to notice here is that this square, being a 2-dimensional object, has its dimensions along the principal axis as well as perpendicular to the principal axis. And you know, when we are dealing with image lengths perpendicular to principal axis, we have to use lateral magnification, and when we are dealing with lengths along the principal axis, we have to use longitudinal magnification. Now, while using longitudinal magnification, I told you to be careful and check whether the object's length along the principal axis is a very small value or a large value. And here if you see, the dimensions given are 1 millimeter, when the radius of curvature is roughly 40 centimeters. So, it is relatively small, and you can use the formula which we have derived. You do not have to once again take these two ends as two different objects and solve, because the dimension is anyway smaller, you can use the formula. Clear? So what I will do is I will name all the 4 corners of that square. I will give them names. So let us call this as A, this as B, C and D. Okay. Now let us try to find the image. So first thing, because this is anyways a small object, so the distance at which it is present, how much is it given as 30 centimeters. So it is given as 30 centimeters. So first what I will do is I will find the lateral magnification. So we know the expression for lateral magnification as f by f minus u. So I will just substitute the values. So if r is 40, we can say that the f will have a magnitude of 20, and because I have considered a concave mirror, focal length of 20 will mean that I will have to substitute it as minus 20 because it is concave. So I will substitute it minus 20 divided by minus 20 minus u is minus 30. So solving this will give me the value minus 20 by 10, which is minus 2. So I got the lateral magnification as minus 2. So minus indicates that the image is inverted. So we know that already. So what we will do is we will first find the final sizes of the image. We will also finally draw the diagram for how the image looks like. So that is also very important in this question. So magnification, lateral magnification is minus 2. Now I can find longitudinal magnification. As I told you, because it is a small object, I can directly use minus m square, and when I do that, I will get minus of minus 2 whole square, which is minus 4. I got the lateral and longitudinal magnification. So which means along perpendicular direction, we can say that final dimension is equal to initial dimension into which magnification should I use here? Is it longitudinal or lateral magnification? Because we are talking about perpendicular direction, we should be using lateral magnification. And when I substitute the values, the initial dimension is 1 millimeter multiplied by the magnification is minus 2. So substituting this will give me the value as minus 2 millimeters. Now once again, minus sign there means inverted image. It is inverted like this, clear? Laterally inverted. Now let us talk about parallel direction along the principal axis. We can say once again the idea is same, final dimension, final length, let us call it as final length is equal to initial length along the principal axis is also 1 mm multiplied by what is the magnification for along the principal axis, which is lateral longitudinal magnification, and we got the value as minus 4. So when I substitute minus 4, I would be getting minus 4 millimeters. So once again I got a negative value. What negative value there represents is that the image formed is inverted once again, but we are dealing with along the principal axis. So how is it inverted? It is inverted this way. So this inversion is represented by the negative sign in lateral magnification, and this inversion is represented by a negative sign in longitudinal magnification. And I told you earlier, this inversion always happens because longitudinal magnification is always negative. In this particular case, longitudinal magnification is always negative irrespective of the sign of m, right. So what that basically means is that, so this object will always get inverted in this manner. I mean the image of that will always get inverted in this manner because longitudinal magnification is always negative, but m can be positive or negative depending on whatever value which we get. So if m is negative, it means this inversion will also happen, up down inversion also happens if m is negative, because longitudinal magnification is negative, left right inversion also happens. So keep that in mind. Longitudinal corresponds to left right, small m, which is the lateral magnification, that corresponds to up down inversion. So whether that happens or not depends on the signs of m. Okay. So, let us now draw the final image. We know that the final image should have a length of 2 millimeters perpendicular to the principal axis and 4 millimeters along the principal axis, right. So, I will draw that image over here. So, if this is the mirror, can you tell me where, can you understand where the final image will be formed, at what distance will it be formed? We know that the object is at 30 centimeters. How much distance will the image be formed? You can directly understand that by looking at the magnification expression which we derived. We know that magnification is minus V by U, right. So, this is minus 30. So, how much should this V be? Minus 60. Then the ratio will be minus 2. So, the image which is formed should be formed at a distance of 60 centimeters from the mirror, and also it should be 4 millimeters along the principal axis, 2 millimeters perpendicular to the principal axis. So, I should be drawing it somewhere over here at 60 centimeters, right. Now, let us decide whether inversion happens or not. As I told you, this will definitely happen. Now, we will have to decide whether this happens or not, which can be understood by looking at this. It is negative. It means that even up down inversion also should happen. So, the image of this will be formed in this manner, right. So, the image will be something like this finally. So, this is how it looks like, clear. So, I want you to think about what would be the naming, the names of the corners which I will have to write here. Remember, both the inversions are happening, this as well as this. So, both have occurred. So, it means that first A will be here and B will be here. When I invert this, so this will be B and this will be A. So, we can say that this will be A dash and this will be B dash, and this inversion has anyways occurred, that is why we drew it below the principal axis. So, this will be C dash and this will be D dash. So, that is how the image will be formed. So, the square plate will get inverted both ways in this particular scenario, and you can write the dimensions. So, this length is 2 millimeters and this length is 4 millimeters. So, if they are asking you the final area of the image formed, you can say that the final area is equal to this area, which is 8 millimeter square. So, that should be the answer for this case. Students, now we will discuss about multiple reflections involving spherical mirrors, right. So, we have already discussed in the case of plane mirrors how the formation of multiple images occurs. So, we understood that when two plane mirrors are like this or even inclined with each other, so the light strikes one mirror and goes on to the other mirror, and we know that whatever is the image formed by one mirror will act as the object for the other mirror, because light appears to come from that image, right. So, the idea is same here as well. So, we have a situation here where we have a plane mirror and a concave mirror, and there is an object which is placed. So, this is a point object. So, this is the object, and they are asking us to find out the image location by considering first reflection at M1 and then at M2. So, we need to first consider that the light coming from the object falls on M1 and then it moves on to M2, and then we will have to find out where the final image is formed. So, what you see here is basically an opaque object which obstructs the light from directly falling onto mirror, because we need to first consider the light falls onto this. So, that is why we placed an opaque object to block the light going onto the concave mirror. So, let us try to find out where the final image is formed after two reflections, first here, second here. Now, you know that whenever if I draw a ray diagram, it is better to understand with ray diagram, although we can directly write equations to do it, but ray diagram will be easier to analyze. So, in this particular scenario, what I will do is I will take light rays coming from here and getting reflected from the plane mirror. So, you know that if I consider a light ray like this light ray will get reflected So, let us consider a light ray like this. So, this gets reflected and it strikes the mirror in that at that particular position. Now, we all know that this light ray after reflection will appear to come from this location, which is the image, and we all know that whatever is the object distance, that will be same as the image distance from the plane mirror. So, this is 10 centimeters, right. Okay. Now, if you look at the light rays which are reaching the concave mirror, so concave mirror will think that all the light rays are coming from this position, right. So, which means this I dash will be the object for concave mirror, right. Whatever is the image formed by the plane mirror will behave as the object for the concave mirror. So, let us write the equation for concave mirror now. So, we know that the expression is 1 by u plus 1 by v is equal to 1 by f. So, if I substitute the values, so u, what is the value of u here? So, this is where the image forms, which is the object for the concave mirror. So, 10 plus 35, so which is 45. So, I get minus 1 by 45 plus 1 by v is equal to 1 by f. What is the value of f? 15, but because it is concave, I will write minus 15. So, that is the expression which we get. So, I will solve this, I will get 1 by v is equal to 1 by 45 minus 1 by 15. So, solving this is going to give me the final value as 45 into 15 divided by 30 with a negative sign. So, 15 ones and 15 twos. So, minus 22.5 centimeters. So, that is where the final image is formed, which means this light ray after getting reflected will reach like this. So, we will reach this particular position, so where the final image will be formed, and this will be at a distance of 22.5 centimeters. So, do not think how do I know this. I can take one more similar light ray from here, do the same thing, and it gets converged at this particular position. So, 22.5 centimeters is where the final image is formed. Now, one more thing which you will have to keep in mind here. Now, in the same case, they can also ask you the other way around. What if the first reflection occurs at mirror M2 and then mirror M1, which means now they are not blocking it. So, let us say in the second case the object is placed, the opaque object is placed on the other side. So, in that case how do I analyze? So, let us draw the diagram once again separately. So, if I take a similar case, so the mirror is over here, same values I am not changing, but the object is this time, the light coming from the object this time will first strike the plane mirror and then move on to the will first strike the concave mirror and then move on to the plane mirror. So, that is what we will have to consider. So, let us see what will happen. So, the object is over here at a distance of 10 centimeters and the remaining distance here would be 25, 35 minus 10, which is 25 centimeters. So, this time I will have to consider the light rays are first incident on the concave mirror and then they get reflected from there. So, first I will directly write the equation for the concave mirror. So, this is case 2. So, what I am writing here is case 2. So, in case 2 first reflection occurs at M, I will write it down. So, first at M2 and then M1. So, I will write the mirror formula to find the location of image. So, I will get 1 by u plus 1 by v is equal to 1 by f. So, 1 by the value of u is minus 25 plus 1 by v is equal to 1 by f minus 1 by how much was that 15. So, that is the expression which we get. So, once again solving this I will be getting the value of v as minus of 25 into 15 by 10, right. So, 5 2s, 5 3s. So, 75 by 2. which is minus 37.5. So, minus 37.5 centimeters. So, that is what we get. So, which means the light rays which are getting reflected from the concave mirror will converge at a point which is minus 37.5 centimeters in front of it. So, we know that this whole length is only 35 centimeters. So, which means the light rays which are getting reflected from here are trying to converge at a point which is over here, 35 centimeters plus another 2.5 centimeters. So, this is that point. So, the light rays are trying to converge here. So, this is what is happening basically. So, this light ray after reflecting from the concave mirror is trying to reach this position. So, this is how the ray diagram would be. Now, these light rays which are incident on the mirror, so all those light rays are appearing to converge at this particular position. So, this acts as the object for the mirror, and you all know what kind of the object it is, because the light rays which are incident onto it, if I draw a similar diagram on the other side, I will understand that it would be like this, and these two light rays will appear to converge at this particular position, correct. So, this virtual object will form an image in front of the mirror which is a real image, which means this light ray will get reflected from the plane mirror and meet somewhere over here. So, I will erase this, this is not required. So, that is what happens in this particular scenario. So, I will repeat once again. So, the object which is placed here, the light rays travel on to the concave mirror, and the image of that is formed according to the expression which we have written at minus 37.5 centimeters, which means from the mirror 37.5 centimeters in front of it. So, this is where the image will be formed, but the light rays in the path of it there is a mirror. So, mirror will obstruct the light rays, making this the virtual object for this mirror. So, now what does that mirror do? Whatever is the distance behind it for the object, at the same distance in front of it, it forms an image. So, the final image is formed over here. So, I can write it down here. Final image is formed at a distance of 2.5 centimeters in front of plane mirror. So, that is the idea. So, in whichever case they give you, whichever is the first reflection, first write the equation for that and take the image, and that will act as the object for the second mirror, and then you can write the formula for the second mirror also. So, that is the method which we will have to use. I hope this is clear. Now, let us see this question. So, similar to the earlier one, so we have a plane mirror and a concave mirror. The radius of curvature is given to us, and there is a point object placed 15 centimeters in front of plane mirror. So, the now question is, find the distance between the mirrors such that the image of the object which is formed is coinciding with the object itself. So, which means the final image which is formed for this object is coinciding with the object itself. So, that is the case which is given to you. So, there are many ways in which this can happen. I'll tell you one case where this might be possible. So, what can happen is that whenever you see this image is formed at the object itself. So, there is one important thing which should come into your mind, and that concept is what we call as retraceability. Now, what retraceability means is that every light ray has this property. For example, let us consider a scenario like this. A light ray is incident in this manner, right, and if it gets reflected by some surface over here, it moves like this along this path, it gets reflected once again here, moves like this, again another reflection and moves like this, and so on. So, in such a scenario, what happens is that if you consider that this light ray at this position reflects perpendicularly, let us consider that it goes and strikes another mirror perpendicularly. So, if it strikes this mirror perpendicularly, what is going to happen? It will just go in the opposite direction in which it has come. So, if it is traveling like this, after reflection it travels like this along the same path. Now, when it follows along the same path, what happens is that not just here, at each and every path which it has traveled earlier, it goes in the opposite direction. So, if reflection occurs perpendicularly at one point, it just retraces its path altogether back to the initial position from which it has started. So, it started from here. So, it traveled like this, but because the reflection here is occurring perpendicularly, it just goes back following the same path, same direction, opposite direction, and it returns back to the initial position. So, this concept is what we call as retraceability of light ray, right. So, this is what should come to your mind first whenever you see that image and object are coinciding with each other. So, this can happen if the light ray which is coming from this object strikes this mirror, goes on to that mirror, and somewhere in between, wherever it can happen, we are not sure about it, somewhere in between, if something like that happens where it just strikes the mirror perpendicularly and then returns back, then in such a scenario we can say that the light ray retraces its path. And so, in this particular case, let us try to apply that particular concept in this case, right. So, this light ray after reflection, we can say that so now let us try to apply that concept in this particular case. We know that the light ray which is coming from this object will undergo multiple reflections between these two mirrors, and somewhere in between those reflections, if the light ray strikes the mirror perpendicularly, so we can say that in such a scenario the light ray retraces its path and goes back to the point where it started from. So, I will apply that concept. So, I will consider that a light ray which is coming from the object first strikes this mirror in this manner, and it reflects from here and strikes it in this way. Now, we all know that this light ray appears to come from a point which is behind the mirror, which is at exactly the same distance of 15 centimeters. Now, think about if retracing has to happen here, if the light ray has to turn back in the same direction here, when will that happen? We know that it will happen if here it strikes perpendicularly. Now, when will it strike perpendicularly? This light ray will strike perpendicularly if this light ray appears to come from a point which is the center of curvature of this mirror. I will repeat once again, if this point is the center of curvature of this mirror, then the light ray which appears to come from this particular point will strike the mirror normally. It means that it just retraces in the opposite direction, and it just goes back, once again reflects here, once again retraces its path, and the image will be formed at this position. So, that is the idea. So, this is what happens. So, now you can easily find out what this length should be. So, we know that this is 15, this is 15, and we need to find this length, which is some d, let us say. Now, I have told you that retraceability will occur if this point behaves like the center of curvature of this mirror, correct. So, if this is the center of curvature, then this whole length from this position till here should be 40 centimeters, which is the radius of curvature. So, 15 plus d should be 40. So, which means we will be getting 30 centimeters plus d is equal to 40. So, d is equal to 10 centimeters. So, that is the basic idea. This point should behave like center of curvature. So, if that happens, then the light ray retraces its path and forms the final image at this particular position, right. So, that is the idea. There is also one more way. If you consider multiple reflections, even more reflections, if you see here there are 3 reflections that we have considered, 1, 2, 3, and finally the image is formed. You can consider a similar case on the other side as well. I will draw that scenario here. So, there are multiple possibilities. So, you will have to check for each and every possibility here. So, if I have the mirror in this manner, so just like I have taken the first light ray to be striking the mirror M1, I can take the first mirror to strike when the first light ray to strike the mirror M2. So, in such a scenario, if the object is over here and a light ray which is incident on this mirror, you know, if the retraceability has to happen at this mirror, it should strike this mirror perpendicularly, correct? If it has to strike this mirror perpendicularly, you know how it should move? After reflection, this light ray should become parallel to the horizontal principal axis. Is that clear? So, when this light ray starting from the object, if it strikes the mirror and if it becomes parallel in this manner, then what happens? It strikes the plane mirror perpendicularly, which means it retraces backwards, and the same thing happens. So, it strikes back once again here, it retraces its path, and the final image is once again formed at the same location. So, we can consider the retraceability to happen either at this mirror, which is this case, or this case. So, these are once again two cases. This is case 1, where the retraceability is happening at this position, and this is case 2, where the retraceability is happening at this position. And now you can easily tell, for this case to happen, how much should this distance be? Think about that. Tell me, from which position should the light ray come so that after reflection it becomes parallel? It should be the focus, right? So, this point should be the focus, right? So, if that is the focus, how much will this length be? We already know the radius of curvature as 40 centimeters, which means this length should be 20 centimeters. So, in the case 2, this length should be 20 centimeters. Is that clear? So, if this is 20, they are asking us to find out the distance between the mirrors. Okay, even in this case, they are asking us to find the distance between the mirrors. So, total distance in this case is d plus 15, which is 25 centimeters, and total distance in this case will be 20 plus 15. So, in this case the total distance is 35 centimeters. So, that is the idea. So, we have considered two cases, retraceability happening at two different cases. So, please keep this in mind. So, this is applicable for any light ray, wherever perpendicularly, wherever it strikes the surface perpendicularly, it just goes back at each and every path in the opposite direction and reaches the source.